Now, what are the things that we are going to be covering in this particular session? Anyway, after this session, I will be conducting a small prerequisite test. Means the test going to be on your prerequisite or this networking fundamentals, just to have an understanding how good you are on the fundamentals part. That is going to be an eye-opener that will also help us in understanding, do we have to update or do we have to refresh that content or not? So, or else you may also be preparing on your own. That's a different story. Okay. So after this lecture, I will be conducting a test, right? That will be purely based on your prerequisite or the networking fundamentals content. Anyway, so introduction to Juniper Operating System. What is the Junos? Junos is nothing but an operating system developed by Juniper to install on Juniper based devices, right? All of your Juniper devices runs with this Junos operating system. Let's try to understand what is that. So I'm Gopi Venkatesan, your trainer, right? So for any communication with respect to the clarifications, you can write an email to gopi@learnpronetworking.com, or you can also write an email to kvgopi@gmail.com. So Junos OS fundamentals. First of all, we need to understand what the operating system is capable of. What is the architecture which is being followed? How this has been adapted, means how this is being beneficial to be installed on Juniper based devices with respect to forwarding the traffic between the interfaces, right? So that is what we are trying to understand here. The Juniper operating system, right? So we are going to be understanding the architecture. There is something called as control plane and forwarding plane. Then we will also understand what is transit traffic and then exceptional traffic and different types of products from Juniper. So first of all, product families. So we have variety of products in Juniper. Now a couple of things. You have router family, you have switches family, you have firewalls. You also have dedicated applications based on Juniper devices or Juniper operating system, right? So what a router can do, a router is a kind of a device which is capable of forwarding the traffic between different networks according to the layer 3 forwarding table. How this layer 3 forwarding table is going to be populated or created, and what is the difference between routing table and forwarding table, we will all see those things in this lecture itself. We also have switches. The switches also runs with, what is that called? The Juniper operating system. We have firewalls. So Juniper has acquired a company called as NetScreen. Because of that, they got NetScreen operating system or Screen OS, right? So Juniper has a policy that all of the Juniper devices supposed to be running with the same operating system, which is Junos, Juniper operating system, right? So what they have done is they have migrated the Screen OS firewall devices into Junos based firewall devices. That's where we got SRX, right? SRX. So Juniper has routers, Juniper has switches, Juniper has firewalls, Juniper also has some of the applications as well. So in routing, again, depending on the sector or depending on the industry or depending on the performance being expected, you have variety of series. See, you have ACX, you have MX, you have PTX, you have M series, you also have T series, and you also had something called as a J series devices. Nowadays, it's not there. This has been discontinued. J series is a basic model of routers that can be found in small to medium business kind of an infrastructure, right? So these are all high performing routing families, routing devices. Same way, we also have switches. You have EX series switches, you also have QFX series switches. EX series switches basically meant for the enterprises, whereas the QFX series are for the data centers or the cloud based, whatever you build it. Now the security family, as I said earlier, you have SRX series. So when I say series, what is that I'm trying to mean it as? You have base model, you also have a high-end model. Base models could be used in the access layer, high-end models could be used in your distribution or core layers, right? Same way SRX, you have basic model as well as the high-end models. So depending on the need, depending on the requirement, either you may be going for a small model or the basic model, or you might be going for intermediate model, or you might be going for the high-end models. So the benefit of learning this Juniper operating system, if you have these kind of devices in your infrastructure, you will be in a position to work with all these devices. Though you may not be able to understand the advanced features. For example, if you are going to be working with SRX, the basic command line interface is going to be identical like Juniper switches as well as Juniper routing families, right? So the basic command line is going to be the same. If you want to be familiar with how to configure, monitor, troubleshoot the security related packages that is available on SRX, that you have to learn separately. Same way, if you're coming to the switching, the basic concept of working with the Juniper operating system is identical. But if you want to work with the switching related concepts, that you have to learn separately. Same way routing, again routing is going to be separate family, but still the operating system is going to be Juniper operating system. The same Junos is going to be running. Okay. Now let's get into the Junos fundamentals. From where the Juniper operating system got built. So you have FreeBSD, right? So you have something called as what? FreeBSD or Linux. So based on FreeBSD, the Juniper operating system software is based out of FreeBSD or Linux. It is modular operating system in what way? Right. For example, if I ask a question, when you are troubleshooting Windows based issue, a client is reporting that he is having some problem, or you might be using a Windows based machine. The most common popular troubleshooting method is what? If you restart your appliance, you restart your laptop, restart your PC, restart your server, most of the problems could be solved. So ultimately what we are trying to say is, if you would like to solve the problem on Windows based systems, one of the common popular troubleshooting method is what? Restart it. All the problems could be solved. When it comes to Linux, it is not the case. Of course, if you restart, the problems could be solved. Now, why is that on Windows based platform itself, it is working fine like that? If you restart, everything will work fine. Why is that? See, because the Windows operating system is based out of DLLs, right? While you're starting up your operating system, all the dynamic link libraries are going to be initialized. They have the link for each and every module. So if for some reason, if you're installing a new software, how this has to work, that link needs to be updated in your DLL. That's the reason if you have installed a new application, you have to reboot your operating system as a whole. When it comes to Linux or Unix, each and every service, we call them as what? Daemons, right? So daemons, they work in a protected independent space. What I mean to say, assume that you have a socket. Okay, let me open up my browser, then I will show you something. Now let me go here. I'm just going to be taking one of those options right here. I'm just opening up both the boxes. See here, I have a spike buster, right? So I have how many sockets? 1, 2, 3, 4 sockets are there, right? So how many sockets I have? 1, 2, 3, 4. I also have an on and off switch. Now what I'm planning to do here is, I have 4 sockets. I can connect 4 devices. The moment I turn on this switch, all of the 4 devices will be getting the power. Whether you are going to be turning on those devices or not, all of them will be getting the power. For some reason, if this switch has a problem, whom all will be affected? All 4 devices would be affected. I'm not sure whether you guys are familiar with the 2-in-1, 3-in-1 systems. Earlier days, we used to have 2-in-1. That means tape recorder and a radio. Later, we got 3-in-1, CD player, tape recorder, and also the radio. That means 3-in-1. Three different components integrated into a single appliance. Right? If something goes wrong with the power socket, or if something goes wrong with the motherboard, what will happen? All 3 components wouldn't work. Now, if I take a different spike buster altogether, see here, I have a separate switch. Now what I have a separate switch for socket number 1, separate switch for socket number 2, separate switch for socket number 3, and separate switch for socket number 4. Now what is the advantage of using this kind of a socket? All I have to do is, whichever the service or whichever the device that I would like to power on, I can simply turn on only one single socket I want. So I turn on the socket number 1, I can turn on the socket and the device which is connected to the socket number 1. If something goes wrong with this switch, this is not at all going to be affecting the other sockets. right? Later on, this is what people started calling it as what, a blade architecture. You can install any blade, and it's the software blade. I'm talking about the software blade. Every software is going to be running on its own protected space. Because of that, if something goes wrong with that, it is not going to be impacting the other modules running on the same device. Same way, if some other module has some problem, it no need to affect my module. So that is the advantage of going for a socket based system kind of a thing. So what I mean to say, when you have a Juniper, there are different modules are running independently. Because of that, any configuration or every service is going to be running its own in its own protected space. Because of that, if one fails, it is not going to be affecting the other modules functions. That is the advantage of going for what? Junos software. Because we have modular operating system, which is like a socket, if any new services needs to be connected, or if new devices needs to be connected, I can plug in. I can unplug one of the device, I can plug the other device and turn it on. That's it. You want to restart one of the module, you can do it. It is not going to be affecting the other. So that is the advantage of going for modular operating system. What I mean to say, if you go back to our product family, you have Juniper routing family, Junos switching family, you also have Junos security family. All of them are running with the base operating system as Junos. On routing family, on top of Junos, the routing package is running. It's a separate module. On switching family, you have Junos as the base operating system. On top of that, you have a module called a switching module. You understand what I'm saying? So on security families, you have Junos operating system. On top of that, the security package has been installed. Hope you understand what I'm trying to explain here. Okay, so this is the key point actually that we need to understand. The second thing is, all of these Juniper devices runs with the same operating system. Just now I'm explaining the same thing. Just now I explained it. Means you can have any of the products from Juniper. The base operating system is common, is identical. So you no need to remember where this command, what command I have to use to monitor the interface. Be it router, be it switches, be it security devices, it doesn't matter. The command is going to be the same, right? Monitoring is going to be identical, debugging is going to be identical, right? So that is the advantage of having a common operating system running on all of the devices within Juniper product families. Like for example, if you take Windows based machines, Windows based operating system, you can run different applications. All of them are going to be little bit identical. You will have file menu, you will have edit menu, you will have view menu. In file you will have new, you will have open, you will have save, you will have save as. The functionalities are going to be identical across different applications. Right? So you no need to learn each and every application individually, where this open menu is available, where this close would be possible, where is that save button. I don't need to practice, or I don't need to remember this on each and every application separately. They have an identical format, right? So the same logic applies in Juniper operating system as well. So if you are familiar with the Juniper operating system, you can work on all of the platforms from Juniper to a certain extent. Now, as I said earlier, it is based out of what? FreeBSD or Linux, and modular operating system. It can accommodate new functionalities. All I have to do is, so for example, in earlier days, what we normally call them as a new module is going to be added. What we have to do, we have a socket. All we have to do is what? It is scalable, it is modular. Any new functionalities, develop and create a new socket, attach it. That's all. So this Juniper software is modular as well as scalable in sense. Now let's try to understand what is this control plane and forwarding plane. This is where the unique difference of what the Juniper operating system's architecture or Juniper devices architecture varies. Now what is control plane and what is forwarding plane? Let me give you an example. Now see, while you are playing any of the game, right, so, or else you would like to move your hand from top to bottom, right? Do I have to focus on my hand that to move the hand from top to bottom? It automatically happens. The command is going to be given by the brain. The hand is going to be acting accordingly. Compare your hand with the interfaces of your Juniper devices. brain as the control plane who controls all of the components which is available on the devices, like your processor. What a processor can do, if processor is missing, though you have all of the components available on your devices, it is brain dead. Nothing could be possible, right? So you have a control plane and forwarding plane separation in Juniper devices. Let's try to understand them. See here, the clear separation of control and forwarding plane since the hardware level as well as on the software level. People who are familiar with Cisco, they have something called as process switching, cache switching, and also topological switching. So process switching is nothing but the forwarding table, or what you call it as a routing table, right? RT here is nothing but the routing table. FT is nothing but the forwarding table. You can see that the forwarding table is built from routing table, whatever it might be. You have something to some information with which the traffic is going to be forwarded, right? Now that forwarding table is under the control of the processor. Assume that. Now what happens, you might be having multiple interfaces on which you might be receiving set of traffic, incoming traffic. Every packet needs to be forwarded out via the other interface, because router is an intermediary device, so it can take the traffic from one network and it can be forwarded out via the other network. Which of the interface it has to be forwarded needs to be decided by the processor by comparing the routing table or forwarding table. As of now, we don't know the difference between routing table and forwarding table. Let's keep something in mind. I have some table. Based on that, the traffic is going to be forwarded. I received some traffic on an interface. Who has to make the forwarding decision? Now the processor has to make the forwarding decision, because the table is under the control of what? The processor. So every packet comes in will be forwarded to the processor or punted to the processor for making that forwarding decision. Hope you understand. Now, if hundreds and thousands or millions of packets are being sent and received between the same client and same server, still the packet, every packet received on an interface needs to be given to the processor for making that forwarding decision. That is what we typically call it as what? Process switching. Later on, we identified that this is not efficient because the packet needs to be waiting in a long queue to be processed. So that's where we came up with something called as cache based switching or cache switching. Cache can hold most recently accessed information in a temporary buffer. So what happens if a packet comes in and this packet is the new packet of a new connection, the first packet of a new connection. Now what happens? I have to forward it to the processor for making the forwarding decision. If the processor says, okay, go out via this interface, that information can be extracted and stored in the cache. Further packets can be forwarded based on the cache without disturbing the processor. This is the advantage of going for cache based switching. But they have some problems. In cache based switching, we face some problem. What is that? Cache memory is limited in size. If the cache is full, the oldest entry is going to be removed, though it is active. In a highly productive environment, you can see that the entries are being removed and added. As an existing active connection entry has been removed, the packet belongs to that connection, has to be forwarded to the processor. Again, the same problem coming into picture. So that is where topological based switching come into picture. So what is the topological based switching? Okay, now basically in topology based switching, what happens is we need a lot of information for forwarding the traffic from one interface to another interface. Now let's assume that I'm going for a router. Okay, let me go there, then type a router. Okay, now I'm just taking this router. This is MX series. Okay, let me take this router. Now there are so many interfaces, right? Okay, now let's assume that something is connected here, some network is connected here, right? Some routers or some network, something is connected here. Now what I'm trying to say here is, when you receive the packet on one of the interface, what this router will do? my MX series router, what it will do? The Juniper router or Cisco router, any router. First of all, it has to open up your layer 1. OSI layer, physical layer needs to be removed. Then it will verify whether the destination MAC address is matching my received interface MAC address or not. If it is matching, only then the further processing could be possible. If it is not matching, the packet is going to be simply dropped over there itself. Right? So obviously, when the packet is being received from one network and it has to be forwarded to the other network, layer 2 MAC address, the destination MAC address will be this interface MAC address. So when the packet is received, layer 1 has been removed, layer 2 also has been removed, and then only the router can realize that the received packet is not meant for me. It has to be forwarded out via the other interface. Now I have to consult the routing table. The routing table may say that the packet needs to be forwarded out via the other interface. Because the layer 1 header and layer 2 header has been removed, before I send the traffic out via the other interface, I need to reconstruct the layer 2 header and the layer 1 header. I don't have a choice. You understand? So because of that, what happens, it has to identify the source and destination MAC address or any layer 2 information. So to do that, you have to initialize one more process. For example, if it is Ethernet, obviously I need to send an ARP message to get the destination MAC address, and then I need to reconstruct the layer 2 header. Now the problem here is, if this is going to be happening in each and every hop, this lookup delay is going to be increasing. So in topology based switching, what Cisco did is, or any other provider, topology based switching, here we call it as control plane, data plane separation. Even before any packet has been forwarded to any of the destinations available in my forwarding table, I will keep all the informations ready to forward the packet via the other interface. Right? What I'm trying to say, if the packet needs to be forwarded out via this interface with the next hop address of so and so, right? What is the layer 2 header I need? That information is ready. So as the packets are coming in via one interface, it has to be forwarded out via the other interfaces. I'm keeping all the information ready, then it will be forwarded immediately. So basically what I'm trying to say, the key difference between the routing table and the forwarding table is nothing but routing table, all possible routes. When it comes to forwarding table, best routes with all the set of information required for forwarding the traffic, even before I receive a single packet for every destination in my routing table. You understand what I'm saying? Right, I receive a packet on one of the interface. It is meant for a specific destination. I don't know what is my next hop address. I need to do the lookup. The routers do something called as recursive route lookup. Okay. Now, those lookups will be done and the information will be kept ready. What is my egress interface? What is my layer 2 header information? After the TTL value got decremented, what will be the CRC? Those kind of verifications, all of them are going to be kept ready in my forwarding table. Because of that, on Juniper devices, the traffic can be forwarded at wire speed. What I'm trying to say at wire speed is nothing but assume that you don't have a router. At what speed the traffic would have traveled, the same speed the traffic will be forwarded, even you have a Juniper router over there. Does it make sense? So control plane and forwarding plane, you have an internal link which is separated in Juniper. The architecture wise, it is built like that. Whereas in other vendor product, it is not on most of the platforms. So in Cisco, we call this as Cisco Express Forwarding. Hardware is not prepared for that in low-end devices. And high-end devices, yes, they are. But the OS is also not built as a separate control plane and separate data plane on all of the platforms in other vendor platforms. Juniper, from the scratch, it is built like control plane is separate, data plane is separate, and there is a link between control plane and data plane, which is an internal link. There is no external connectivity needs to be given. Right? So the routing engine is what the responsibility of the control plane, and packet forwarding engine, or else we typically call it as PFE, which is responsible for forwarding plane. Let's see one by one. Now, what is that control plane? Manages the routing and forwarding tables. Just now I told you what is routing table and what is forwarding table. Routing table, we typically call them as a RIB, routing information base. When it comes to forwarding table, which is called as a FIB or else forwarding information base. So forwarding table is going to be built from routing table. Okay, the best routes, whatever are available within your RIB, is going to be picked up and copied into your forwarding table. Based on that, the traffic can be forwarded. While the traffic is going to be forwarded based on the forwarding table, some of the additional informations are required. Those informations are also going to be kept separately in forwarding table. So who is going to be responsible for maintaining the routing table as well as the master copy of the forwarding table is control plane or routing engine. And manages the routing and forwarding tables, that is a key point. Manages the PFE. What is the PFE? I just go back to my previous slide. See here, you have a forwarding table, and this forwarding table is nothing but the copy of your routing engine. You understand? You have a forwarding table which is built from routing table. I call this as a, I'll do one thing. See here, this is going to be considered as the master copy of the forwarding table. If I'm going to be having a single copy, then everybody has to wait in a queue. Because of that, the control plane will make a copy of this forwarding table to the forwarding engines or packet forwarding engines. How this is going to be happen, how many engines would be, how many PFEs will be there, are purely dependent on the models. It is not that every model will have 2 PFE or 4 PFE, not like that. Now for example, if I say, if you have, let's say, let me go and open up, what is that called, my whiteboard. See here, if I have a 24 port switch, I don't know whether you have that experience or not. Let's assume that you have a 24 port switch. Okay. Now all this 24 port is going to be part of this PFE or single PFE or more than one PFE. It purely depends on the model. Okay. Now basically what I'm trying to say is, if you have a single ASIC or the single PFE, this is what I'm calling it as a PFE, which governs all the 24 ports. Now what happens, any traffic received on any of the interfaces of this switch basically needs to consult the forwarding table, which is part of this PFE. Now every packet will go to the PFE for making the forwarding decision. If something goes wrong with this PFE, all 24 ports will fail. Now what if I have 2 PFEs or 2 ASICs or 4 ASICs? Now, if you have 24 ports and 4 ASICs are there, then every ASIC is responsible for managing 6 ports. When I have 24 ports, 4 ASICs, every ASIC is responsible for 6 ports. If one ASIC fails, what would happen? Only that associated 6 interfaces will not function. The rest of the 18 interfaces will function. Now, this PFE is going to be getting a copy of the forwarding table from the control plane. Is that clear? That control plane keeps the master copy of the routing table as well as the forwarding table. Does it make sense? Anyway, so we are talking about the control plane, and it is responsible for managing the PFE. In what sense? Any updates with respect to the master copy of the forwarding table will have high priority to synchronize this information with the PFE. See, there is a change in the routing table. Because of that, there might be some changes in the forwarding table. If there is a change in the forwarding table in control plane, that has to be synchronized with the ASICs or the PFEs. That is going to be having the highest priority. That is what I'm trying to mean. That is where this manages PFE comes into picture. Also, it manages the chassis while you're monitoring for environment, heat. All of them are going to be responsible of your control plane. Right? Then we also have the forwarding plane. Basically, a forwarding plane is going to be having a copy of the forwarding table. Upon receiving the traffic, it is going to be forwarded out via the other interface by comparing or by looking into the forwarding table locally available on the PFE. Now keep this in mind. So in Juniper, the PFEs comes with a separate processor, separate memory, right? So because of that, the cards here, we call them as PIC, physical interface cards. Okay, those physical interface cards are costlier than any other vendors in the industry, because they have a separate memory, separate processor, separate everything is individual, right? Assume that you have a PC Within PC you have multiple processor, and every processor is going to be allocated for some other function, something like that, right? So the forwarding plane's responsibility is what? Simply forward the traffic between the interfaces according to the forwarding table I received from the control plane. Then if additional services like your quality of services, access control list, any additional services you would like to implement, that gets implemented on PFE, not on control plane, right? So any additional processing on the received traffic is going to be done through the help of additional services. Those services are implemented in PFE, not in control plane. Don't forget that. Now this takes us to differentiate different types of traffic, which is transit traffic and exceptional traffic. Before I move on to the next slide, I will explain you what is transit and what is exceptional. Okay. You guys might have traveled to different destinations. Okay, let's say that from Chennai to Hyderabad, I can take a direct flight, right? I can take a direct flight. People who are traveling to Hyderabad, they will pick up the flight. The destination itself is the Hyderabad. Now, assume that there is a flight going to Delhi, stops in Hyderabad. Now what happens? People might be dropping in Hyderabad, or people might be going to Delhi. So from Hyderabad's perspective, people who are traveling to Delhi is considered as what? Transit passengers, right? Whereas people who are entering into Hyderabad, they are called as what? Exceptional traffic. A router may receive the traffic which is meant for itself, or it is meant for someone else. For example, let's assume that 3 people are there. Let's go to my whiteboard. I have a router 1, I also have router 2, I also have router 3. Now, I receive a traffic on one of the interface of the router. Now, this router may be forwarding the traffic to a different destination. Might be, I'm not sure. Or this administrator is trying to logging into the router. Now, in this case, if the traffic is meant for a different device, the router receives the traffic and forwards it to the other forwards it via the other interface. This traffic from this router's perspective is called as a transit traffic. If an administrator is trying to logging into the router, management plane or whatever it might be, telnet or whatever he is doing it, in that case, the traffic is meant for the router itself. We call it as exceptional traffic. Does it make sense? Exceptional traffic is nothing but the traffic meant for the device itself. Some of the example, assume that you are going to be running some of the routing protocol between these 2 routers. Now what happens? The traffic comes from here, goes to here. It's meant for the device itself, right? So the receiving router, it's going to be processing it. It is not going to be forwarding it. From this guy's perspective, that is going to be considered as an exceptional traffic. Whereas now an administrator is trying to logging into the 3rd router, which will go through router 1 and router 2. So from router 1 and router 2's perspective, that is a transit traffic. From router 3's perspective, it's exceptional traffic. Now let's move on to the presentation. So we know what is transit traffic. Traffic forwarded according to the forwarding table. Now the forwarding table, where and all the forwarding table will be there? You will have a master copy of the forwarding table on the routing engine or the control plane, and you will also have a local copy of the same forwarding table in every PFE that you have. So the traffic is going to be forwarded according to the forwarding plane, forwarding table, and which is called as a transit traffic, because the traffic is not meant for the device. Whereas exceptional traffic, the traffic which is meant for the device itself. Now somebody is doing something like management traffic or routing protocol updates, all of them are meant for the device itself. So though the traffic is received via an interface, it has to be given to the CPU. Because of that, some updates could be happening. Somebody could manage the device. So traffic which is meant for the device itself is called as what? Management traffic, exceptional traffic. The traffic is going to be received on one interface and forwarded it out via the other interface. We call that as what? Transit traffic, right? Now the traffic which is going to the control plane or the routing engine is going to be rate limited. What is that rate limiting? We have a bandwidth limitation, how much traffic can be, how much bandwidth of this internal link could be utilized for sending the traffic to the control plane. Why is that so? People might be launching an attack, right? I don't want the internal link to be overutilized. Because of that, the control plane might be busy due to that attack. I don't want that to happen. That's the reason the traffic which is going to the control plane from your forwarding plane, you have a rate limiting. Okay. Now, so what is that we understood on this presentation? We understood the Junos software architecture and how the traffic is being handled. We know what is the control plane. We also know what is that packet forwarding engine or the data plane or the forwarding plane. And we also understood the transit traffic and exceptional traffic. We identified different set of Junos platforms in Juniper. Right? So that's the end of this first presentation.